Hi, everyone. Thank you for joining today's presentation. I know we've got people joining in from the waiting room, so I'm going to give everyone just a second or two before I get into the webinar. Let's see, I think people are starting to join. So while you're joining, I'll announce our presenter, Christian, today with ATOS. He is presenting Reducing Operational Carbon Emissions and Increasing Energy Efficiency with Solar Air Heating. Now, a few things about today's presentation. It is AIA approved. So if you were not able to submit your registration number during signing up, that'll be the first link I'll drop in the chat. That'll be a good way to ensure you receive that one credit for joining today's presentation. Second thing, there will be a webinar poll that we launch about 45 minutes of the way through. That'll be a really great way to connect with Christian, Jason, and other members of the ATOS team after today's presentation for anything you may need regards to price quotes, product literature, samples, or just general more information. And then there will be an optional Q&A at the bottom. You can also send it to me in the chat. If we have time at the end today, we'll give some time to answer a few of the questions, but if not, they will be able to reach out to you after today's presentation. And then, Christian, would you mind unsharing your screen for me?
Yep.
Okay, one more thing. This is where you can find ATOS's brand page on Acelab. This will be the second link that I'll drop in the chat. A great way to get in contact directly with Jason here, the Architectural Business Development Manager, as well as find out more about their products, save any tier schedules, and then get any of those certifications you're looking for. And then that final link I'll drop in the chat is a good way to request things like lunch and learns or office presentations with ATOS. So 3 total links. And that's the end of my spiel. I'll let you take over screen share, Christian, and whenever you're ready to get started.
Thanks very much. So, hello, everybody. This is Christian Vachon speaking, live from Allentown, Pennsylvania, the headquarters of where ATAS is located. ATAS is a family-owned company that's been around for 60 years, and it stands for Aluminum Trims and Shapes. It was founded in 1963 by Jack Buss, the father of the current owners of the company and grandfather of the current owners of the company. We have 4 manufacturing plants across the United States, as you can see, across the board from Allentown to Mesa, Arizona, University Park, Illinois. And yeah, it's basically been a family-owned business, and the feel that comes with it, also with customers, that's also part of our history and everyday life. So basically what ATAS does in a nutshell, I mean, anything that basically covers metal cladding on roofs and walls, as you can see here, and with different accents, corners, different shapes, trims, accents for interiors as well as exteriors, perimeter, insulated metal panels, accessories as well, different types of accents as well, different colors, and a whole set of tools to help you guys, engineers and architects, to do your designs with assistance in all sorts of resources, which you can find also on the atas.com website. So one thing that we do as well is solar air heating. Solar air heating has been around for a long time, and it's pretty simple and efficient. We're going to have a look at this today together. And so basically, in a nutshell, we're going to understand how it works and have a basic idea of how we can design around solar air collectors and where they do come in play and be useful, and how it cuts carbon from emissions that you have in your buildings. So in a nutshell, that will be it. And hopefully at the end, you will be able to talk about it a little bit more. So why do we say that transpired solar? Transpired basically stands for a perforated panel. There are all different types of solar air collectors on the market, but the most common in North America, Canada, and the US certainly is a transpired collector. We're going to go into that later on, but it's simple. Basically, it's a perforated plate. It's efficient. When we say efficient, we mean It converts solar energy into warm air at a rate of about 90% or up to 90%. If we compare it with other solar technologies like a solar pool heater or a solar water heater, they're about 65% efficient. We get up to 80, 90. With regards to photovoltaic panels that do produce electricity, of course, they do produce something else than warm air, but they're about 15, 16% efficient. So we're a highly efficient technology in terms of converting solar energy into warm air. So if we look at basically greenhouse gas emissions across the country, we can say that 35% come from buildings, from according to the administration. So and a lot of the energy that goes into buildings and all our energy needs across the board every day, very little still come from renewables these days. So we're in the fossil fuel age, but renewables are making their way. And if you look at within the part of renewables, solar air also occupies a small part. So there's a lot of room to grow. We can put it that way. Now, in terms of building energy consumption, solar air will really be in a position to help you with if there's ventilation in the building. So, for example, right now we're looking at a building envelope, and this building envelope has an R value on the roof and on the walls, and basically the heating system that you will put in there that engineers will set in place in there will produce heat enough to compensate for the losses in keeping the temperatures warm inside. So when you look at it with this type of building, with the envelope, without any ventilation, it doesn't cost too much. I mean, it always costs too much, but it doesn't cost that much money. When you start adding ventilation to it, this is basically where it starts getting costly. So heating outside air, the air stays in for a few minutes or maybe half an hour, 2 hours, and then it goes out the other way. Basically, then it requires a lot of energy to heat the outside air from like whatever the ambient temperature is to the set point inside the building. And this is where solar warm air comes into play. We also look on a broad view as well. You see the spikes that happen during winter. Solar air collectors will also help like reduce the energy peaks in winter on a global level once we get there. So although this may be fairly new or innovative to you folks, or some of you, because some of you have worked with it probably, it's been around for about 30 years. In fact, the first installations were at the beginning of the 1990s. So there's no R&D involved in this anymore at all. And there's been, of course, progress since the 1990s, but it's been around for a long time. It's also been recognized by the U.S. Department of Energy and Natural Resources Canada as something that is very groundbreaking almost because it's simple and so efficient. So it's the least costly solar energy technologies, or the most profitable, if you want, per square foot or per watt produced. So the concept of a lanced collector that basically is a transpired collector, you have different types of perforations that you can do. There are different holes and shapes, but the most common profile that we see also in North America is the lanced perforation, because it creates sort of a turbulence around the openings, and also basically it doesn't lose any, because we punch the panel. It doesn't remove any matter, so all the solar energy absorber, if you want, stays within the metal. So we don't remove any matter. We just punch into it, and that creates a hole, as you can see here. Now, the most common colors that you will see or that you can work with are basically black, dark bronze, Hartford green, this sort of color. We also have selective colors. We're going to be talking about that today. People have done, of course, lighter colors, but of course, the more energy efficient you want to be, the darker you want to be. However, we have seen some colors that are on the lighter range, as we're going to see. So transpire may be a word that was created to apply for solar collectors in the 1990s, when there was research on at the National Renewable Energy Laboratory in Colorado. Beginning of the 1990s would be the first time that transpire got into motion as an expression. So what does that do? Basically, reduce energy is basically what we're looking at. That's objective number one. By preheating outside air, it also improves indoor air quality, and you will see that it also will benefit for lead points. So how does that work? So this panel that we saw on the picture earlier that is perforated will be located somewhere in front of an air inlet. So imagine you have a building, air inlet from the wall, and that's the existing wall here. If you can see, the yellow surface is an existing wall, and you're going to be positioning the transpired solar collector away from it by about 4 to 8 inches. And so that's going to create sort of a plenum, and the intake air that's going to be pulling air from into the building, but from the collector plenum, will draw the air through the different perforations. There are thousands of perforations. And so when the air passes through these perforations, it'll basically get the heat from the incoming solar energy. The panel will get warm. The passing air will just retrieve the heat from the surface of the panel and direct it into your ventilation system. So that's how it works. There are many different ways that you can then attach the solar air panel to your HVAC system. I would think of about 60 easily. However, we can show you the two main ones today. So the standalone system is basically a system where you have a fan. It could be with a fabric duct or a metal duct that to push the air in. The fan is connected to the outside wall, and it'll just be pulling in the air from it. And we can also mix it with ceiling air, for example, to alleviate temperature changes and just diffuse the air into the building. It's usually used in open ceiling areas, for example, like work halls and so on. So open ceiling areas are where we install these standalone systems. The other main configuration is the makeup air preheating. So we can see here on the screen these makeup air units that are on the roof. They're dedicated to take in and condition outside air to set points that are, for example, 70 degrees F. So the solar component will be located upstream from the fan and from the gas heater, and then delivered at the set point temperature into the building. But at least it'll be preheated and sometimes fully heated by the solar collector, depending on outside conditions, including solar energy and so on. So that's the second main configuration that we use to this. We talked about, black paint here, or that's black paint. Black paint versus selective. So there was some tests some years ago that we did when we introduced the selective surface into the solar air field. The selective surfaces have been used for solar water heaters for at least 20, 25 years. We don't see that many solar collectors anymore with hot water. So when we adapted to solar air, we can actually bring in the air from outside and take it up to from ambient up to 90 degrees F above ambient on a selective surface. With black surface, we could only go up to 50 degrees F above ambient. So that again does not depend on the season. It's in summer, it's in winter. So if in winter you have like a chilly 0 degrees F outside, we can bring it up to, under certain conditions, to 90 degrees above ambient. If it's 100 degrees out there, in the middle of summer and you want to heat in a process for drying or whatever, you can also increase the temperature above ambient by 90 degrees F. So we measure above ambient regardless of what ambient is, and it works in winter as well as in summer. So that finish comparison that we want to talk about, basically that thermal emissivity is a big factor for a selective surface. So this blue surface, we're going to show pictures. So with black, basically it absorbs 95%. So it'll absorb the heat from the sun and also re-emit back to the environment through emissivity. So basically when you walk by a dark finish or a dark solar air collector and it's not working, you can feel actually the emissivity or the radiation coming in from the panel. With a selective surface, you don't feel it because it's only 3% emissive, so you don't feel anything. When you touch it, however, the panel itself will be much hotter on a selective surface than it is on a painted surface. Any solar air collector, just like solar water heaters and solar PV panels, they have to be certified. In this case here, our collectors are certified through the SRCC, the Solar Rating and Certification Corporation in the US and Canada. For Europe, there is a solar key mark, and both standards are really close to each other. You can see here the collector being tested on positive, negative pressure here with suction cups, to cater for wind loads and that sort of stuff, as well as energy efficiency. So on the panels exposed to the sun, we measure in all collectors the efficiency of the collector depending on sunshine. So that leads basically in the end from test to certification. So any collector that you want to put into your projects has to be certified, and you can go and have a look on the SRCC website, and you can get a list of all the certified collectors in there, whether it be evacuated tube, flat plate water heaters, or solar air transpired heaters. Now, how does that work? And when you see a collector and you think a thermal imagery, this is quite interesting. On the left-hand side, you have a non-active grain surface, basically not connected to any HVAC at all. And on the right-hand side of that building, you have like a black transpired solar collector. And you see the collector in action here. It's actually cooler. So the solar air collector is cooler simply because we extract the heat from the surface of the panel with the passing air. And we can see that actually this one in particular is working well. You can also see here where it's not working as well. You see the joints. That's basically the joints between the sheets where they overlap a little bit. So there's no air coming through, and you can see that it gets a bit warmer in that state. So you can see through this thermal imagery that this particular solar air collector works. And the surface is cooler because we, again, retrieve the heat by the passing air. Now, when we pass the air through it, we get a temperature rise. The temperature rise will vary according to collector through flow. So a through flow basically means the CFM is a cubic feet per minute of air through by square foot of panel. So we go from 2 to 10. So 2 is low flow, 10 is high flow. And we can see here, for example, that solar conditions down the bottom in watts per square meter or BTU hours per square foot, that you see that the more sunshine you have at full sunshine, for example, you'll have like an efficiency that is higher with and a temperature rise that is higher with a high flow. So the high flow has a higher efficiency. The low flow has lower efficiency, but higher temperature rise. And we can see it here with this type of curve. So you can see that the efficiency goes up as we pull more air through the collector, and the temperature rise goes up as we pull less air through the collector. So sometimes, for example, for heat pumps, we will want to go through low flow, high temperature rise. And typically on a makeup air unit project, you want as much energy as you can get from the collector, and you can go at high flow, therefore at high efficiency. There are different types of panels out there. So we've shown a picture, like a close-up of a lens perforation, but you can also do, it could be horizontal, vertical, do different shapes and designs. And that's one example that we can find here in upstate New York, for example. This one is one using the selective surface, and that's up in Canada in an industrial setting. And architects love to know about colors and so on, and integration. For example, you will have projects where your customer may say, I want a solar collector on this, but please, integration, I don't want anybody to see it. Here's an example where you have like a small portion of this surface being a solar air collector, and the rest of it is non-active, and it's fully integrated. And on the other hand, you may have like a collector that requires or will have like many colors and shapes that will sort of fit with each other. So you can see here sort of a blend of mission red as well as matte black on one side, and the other side you have a selective color that applies to it. So through the different pictures, you will see that there are many different possibilities here. When we say simple, basically compared to a normal cladding, metal cladding that you have on the wall, all we need to do is like what I talked about before, that cavity. The cavity space is basically between 4 to 8 inches, goes up to 12 at times, but that's very rare. And so what we do to do that, to achieve that, is we set in this particular case, a set of Z-bars that go up, and horizontal hat bars that come on top of it, and that will create basically the spacing that you need for the air to be pulled in through all the perforations. And so within this substructure here, you can see that there's a horizontal chamber, so we make sure the air gets to the gets to the air intake. And you can also see the same design with a selective surface versus a brown surface. But the framing required basically is very simple. So once you have your air intake facing south, you have the wall in front of it with the canopy and the cavity. You can draw the air through it, and basically the panel will just stay there. And as long as you pull air through it and the sun shines on it, it'll provide free solar heated air for decades to come. So you can see that many different types of collectors have been applied in many different situations. We're going to go through some of them. Right now, for example, this one is an interesting one using a round shape. So round shape facing south between east, south, and west. You can also play with that. So some bend shapes to fit the architecture of the project. This is a school. A school is always a good candidate for solar air heating because we need outside air. There's no school without outside air. We all need air quality. So basically we need air from outside, which needs to be heated. What I like about this picture that it shows two solar technologies side by side, photovoltaic and solar air heating at a school in Maine. Same concept with, again, another type of integration, another school up in Montana. This one is in Minnesota. It basically heats, sometimes it's the gymnasium very often. Sometimes it's the middle hall or if you want the main hall. In this case, on this school, it's the main hall of the school. Higher education will sometimes require, this is like a college near Chicago where they do mechanical equipment education. So they do need outside air a little bit more. This interesting one is like this got a full parapet on the top. It could have been a partial parapet, but it's a full parapet, and we don't see it. But basically, the HVAC equipment behind it pulls the air from the top of the panel, and not from under the ceiling, but on top of the ceiling, above the roof line. Penthouses also good for that. This is again University of Minnesota. The penthouse is basically where you have where you locate the mechanical equipment. And here in that case, the engineers and architects chose the penthouse to have the solar air collector right by the equipment. And it also makes it easy for controls and dampers. And the rest of the building, if it has to be white or glazed or whatever, is not affected by it. In fact, it is actually an advantage to have the building as such and the collector on the penthouse. You can also integrate it with additions, like you can see here, modern versus old, with the collector here acting in the middle versus the old part of the building, which was again added, and this new part here. And in the middle, you have your air intakes, and you can see the equipment on the roof. So that's two sides, facing south, facing west, two sides accommodating for the incoming air, and architecturally pleasing as a transition. We also talk about the industrial applications. Here is one that is a coil coating plant in eastern Pennsylvania. And the interesting thing, again, is to see both solar technologies on the one building. You have the photovoltaic panels on the roof and the solar air collector on the wall. In fact, these collectors are basically located where they should be, as heat is more needed in winter, and the sun being lower in winter, it's better for the transpired collector to be facing the south wall, and it's better for the PV panels to be on the roof. So they can be fully integrated and or separated like that here. Transpired solar collectors can also be used for agricultural applications. So animals do require outside air as well for productivity and for the well-being, of course. And so you can see here some examples of integration of transpired solar air collectors into barns and farming facilities. Transportation. Every time we talk about transportation, transit centers, it could be for buses, trains, automobiles, whatever. Garages, they do need a lot of outside air, basically to renew the air from the combustion and or the welding work that's happening inside. So the higher the outside air requirement, the more a solar air collector can be integrated with success. And in that case, it's the Minneapolis bus garage that was commissioned in 2022 that has sort of panels Even in between here, there are some panels. So you can see the facing west here, some dark bronze panels, and in between you have some dark color, black color in between. So architects can also play naturally, obviously, with the different shapes and forms that are available and integrating a solar air collector. This is a good example. Government, commercial, hotels. So basically here you see like an office building in Germany on the right-hand side with the glazed facade around it, but the solar air collector was integrated in the middle. And you can also see the one hotel here. We won't mention the name. Yeah, and it has like a parapet that goes above the roof. And again, the aim of that extra parapet is to, when you have like it's connected to mechanical equipment outside on the roof, it sort of hides it. So it's an integration, and it also hides the HVAC equipment on the roof and the ducting required to do that. Military, same thing. The U.S. Army has been a steady customer, I guess, of transpired solar collectors over the last 3 decades. Here's one example in Fort Campbell, Kentucky, and same applications again to heat the building and reduce cost and actually increase independence, energy independence, which is something that matters quite a bit. Food processing. Basically, you could dry pasta. You need warm air to do all sorts of operations in the food processing business. Here's a cheese making plant, basically that requires 300-degree air all year round, day and night. So what could be a better application of just, because it needs to have outside air all the time, better application to put a transpired solar collector on it. It's been there for 10 years. And again, it sort of preheats the air as soon as the sun shines on it, reducing the high cost of basically heating air 365 days a year at up to 300 degrees F. So this is a perfect application here. High rises and apartments, also a candidate. You can see here on the right-hand side, this transpired solar air collector on the side of the building on that corner. So that's the tall one here. And then, of course, you don't see the equipment, but it's connected. In this garage, basically apartment blocks on the left-hand side, the collectors are fully integrated between sort of a brick area here. And they can also be used to heat the air that goes into the corridors of the building and also sometimes the underground garage. So underground garage also requires outside air all the time, needs to be preheated. And when you do that, you can also help dehumidify the garage simply because the incoming air is warmer than the environment. So it is not dehumidified, but it's less humid, relatively speaking. So we decrease humidity levels, relative humidity levels, by increasing the temperature through the collector. And in some cases, it does help to heat and also to dehumidify the inside space. Laboratories, same applications. They do often have 100% outside air systems. Again, a perfect candidate to use transpired solar air collectors. You can see here the bypass dampers for summers. So they do open in the summer so that we bypass, if you want the collector, we may not need that warm air 12 months of the year. So that case, you can see bypass dampers. Not to worry about it. You don't have to integrate them in the collector, on the face of the collector. They can also be elsewhere. In this case, they chose to put the bypass dampers on the collector face, but sometimes you don't see them simply because they're located elsewhere. It could be to the left, to the right, west, north, east of the building. It doesn't really matter. It's a matter of design. Drying equipment, obviously, there's just about anything that you can dry with warm air. In this particular case, in California, they dry firemen's equipment through this. So all the equipment that the fire department uses needs to be dried, washed and dried after. And so in this particular case, it's a huge dryer. But they also drying equipment or solar air collectors have been used to dry all sorts of produce and different nuts and so on. So drying is also an application that you can work with. So modular designs, we can see here a modular design, sort of a boxed in collector, which is more like, we're used to seeing PV and solar water heaters on the roof like that. That can be done when you have no possibility. So if your building is good would be good for solar air heating, you need outside air to be heated. However, the wall is not available simply because there may be an extension in a couple of years' time. You have diesel trucks driving in front of that wall all day long, or it's simply because it's a um, historic place where you're located, so they're not going to issue a permit for metal panels. You can still go on the roof. And here's an example. So typically by manufacturers, the roof systems are not promoted, but they're certainly there as a backup. If we can't do it on the wall, we do it on the roof. So it's the same output, maybe a bit more expensive. In fact, it is more expensive to put some A-frames and have these collectors built on the roof like that. But you can also have the chance sometimes to facing due south and facing at a proper angle. So these modular designs do exist, and they do use transpired, that is perforated collectors on the surface as well. So here's a residential application where the transpired collector will be sort of like put into a glazed box if you want. And so it's inside. And it's glazed because there's air from the house or the garage here that will be just circulating through it, and you don't want to lose the heat to the outside. And in this particular case, it also has another type of solar energy here. This is a photovoltaic panel. So the photovoltaic panel will be producing electricity for the fan. So when the sun shines on the panel, electricity is produced for the fan. The fan pulls the air through the collector, and the fact that the sun also is exposed, the collector is exposed to the sun on the thermal side, it'll also produce warm air. And the two will go hand in hand. So basically, depending on solar radiation intensity, the fan motor will go faster when there's more sun. So, therefore creating more heat, more BTUs out of the collector. And when there's little sun, basically the fan will adjust and it'll slow down. And the air passing through the collector will be at a slower pace, therefore still retrieving heat, but at a lower pace. So that's, again, a residential version for you to know. Now, the angle of the sun we talked about, yeah. So depending on the latitude, if you look at northern latitudes close to the northern border, like Spokane, Washington, you can see here that basically the sun will hit a south-facing wall at a good angle in winter, less so in Dallas, Texas. So this is why it's good to look that way, facing south on the wall. You can also do any orientation from east to west. You still get quite good performance from west and east. Southwest and southeast are also good. And of course, our best bet is the south-facing wall. In many areas where you can have an industrial building, you will choose between southeast and southwest. What would you choose? What would you choose as the best? So if you have a solar water collector, it's different. You want the heat in the collector. You want the water to just go through and pull the full sun's power. In the case of solar air, you're better off in the morning being southeast and not southwest, simply because air is crisper, it's fresher in the morning, it's at a lower temperature. So when the sun moves from east at 6 o'clock in the morning to midday facing south and to 6 p.m. facing west, you can see, for example, that during the day, especially during the shoulder season, you will have like lower temperatures in the morning. So a southeast facing wall will give you more input. Whereas in the afternoon, for example, in springtime, it could be warm in the afternoon, and basically you don't need the heat anymore. So you have a wall that is facing west, but you don't need the heat anymore. So you'll open the bypass damper. You will leave that solar energy outside. So typically a southeast wall is better than southwest, and also because it's protected from the wind. So being an unglazed collector, that is no glazing in front of a transpired collector, it is affected by the passing wind. So wind blows on the surface of the collector. The heat that's been removed by the wind cannot be pulled in anymore. So therefore, in that case as well, it's more protected when it's facing east because most winds come from the west. If you're in an area that's the opposite, then of course the opposite reasoning applies. So we come again with this exposure to the sun with, again, PV panels positioning winter solstice. Winter solstice is where you have the lowest, 21st of December in the Northern Hemisphere is when you have the lowest. So what you want to do is you want to also check whether you have like shades on the building. So you want to do a school or an apartment block, but there will be some shades going around. So you want to look into that as well to make sure there's no interception of light for the collector operation. Now, when we compare cities to cities, let's say we have like a roof-facing solar transpired collector used for process heat. We want to dry coffee beans. We want to dry, as we said earlier, milk produce to produce powdered cheese or a pasta that needs to be coffee roast, all sorts of processes where you need heat. If you look at putting it on the roof and you look at the charts, you will see, for example, that Phoenix and Los Angeles would be your first city. So basically, it goes with the solar radiation that you get on per square meter or per square foot of where you're located. And you can see that in the US, most of it is southwest. Does that mean that all these pictures that I showed you from Montana, Minnesota, and New England are not good? No, because they're used for building heat. So if you use building heat, then you need cold. You need the sun, but you also need the cold. So for space heating, it becomes another thing. So you see Denver, Minneapolis, and Chicago between each other. It's relative to each other. If you run a simulation for Denver, in Minneapolis, you'll get 74% of that same result. So you can see here on the map that ties up with the one we've seen before with the sun availability, but also like the degree days, basically the need for heat that you have in your area. And you can see now that Phoenix and Tampa Bay are dead last in that case, simply because there is no need for heat, not because it wouldn't work. We also talked about colors earlier. Again, we've seen colors being used that are close to white, and any color absorptivity will basically give you more power. So it's about as simple as that. And so when you design a project, you can ask, or you can look at the absorptivity of the color you're looking at and match aesthetics with performance. And so that's, as a designer, it is your call. And very often, engineers and architects will just debate between each other, which one should we go for? Again, for engineers, they typically want the best output. When we do energy monitoring, you often see, for example, like the proposed case before, base case before is you have like from midnight to midnight, a makeup air system that requires so much gas during the day in kilowatts of power here. And you have like a trough during the day when the temperature gets high during the day and it up in the evening. And you can see here the solar, I call it the solar bell, if you want, that comes in between. A nice sunny day will just cover part of your load or 100% of your load, depending. So when we see monitoring results, this is typically what we see. And you can see the blue shade, which is gas consumption being reduced. I say gas. It could be oil, could be propane, it could be any form of fossil fuel. And this is why we say that the red part that's occupied by solar will basically decarbonize, that is to produce less consumption of fuel, therefore less burning, less combustion of fuel, and therefore greenhouse gas emissions. So this is how it lowers basically the greenhouse gas emissions in a given setup. So ASHRAE, the American Society for Heating, Refrigerating, and Air Conditioning Engineers, has had standards a long time for indoor air quality, which basically also means the amount of outside air that you need. On a typical project, when working with engineers and specialized providers, the engineer will say, in that specific school, we need that many CFM, again, cubic feet of air per minute of outside air. So the fan size will be determined usually by the engineer. The collector size can also be determined by the architect. So, okay, in this area, this is how much area we have facing southeast or west for that particular building, let's say a school. So here that determines the collector size. And then the collector size and the fan will give us CFM square foot, a CFM per square foot. So we move from 2 to 10. So then we can also adjust porosity. And in the making process of transpired solar collectors, in some cases, we can adjust the depth of perforations, that is basically the opening area for the air to flow through. And the plenum depth will also be determined relative to the geometry of the wall versus the fan. And these are basically all candidates that you can think of that do require outside air. So all these different applications here are out there. Laboratories, of course, come again and again. If you work in the pharmaceutical industry and so on, we have clean rooms. They do require a lot of outside air. The perfect candidates for transpired solar collectors. You can see here, and you can find them, these clean rooms in different aerospace, pharmaceutical, military, defense, and so on. So if you have that, that typically is also good. Spray booth, paint shops, anything that requires outside air is also very, very good. One of the things we do as well is we want to make sure that we don't increase the air conditioning load. And then basically engineers ask us pretty often, like if I put a solar air heater on the south-facing wall, am I just transferring the heat into the building? In fact, the south wall is more protected when there is a collector in front of it because it provides shading. And also, because it's perforated and because air rises on its own, through the thermosiphon effect, basically the collector cools itself. So not only does it provide extra shading on the south-facing wall, but it also cools itself in summer when the sun shines on it by getting in motion that buoyancy effect, the thermosiphon effect. We also use a nice optional benefit during nighttime. So because the collector emits towards outer space, if you have like a painted collector, facing south, but it also is going to be half of it's going to be facing space during nighttime. Nighttime faces outwards to the sky. The sky is infinitely cold. There's no actually heat up in space, which is basically what the collector sees for half of its surface. And so we do see cooling of a subcooling of the collector at night, and we can use that as an option to subcool the building and let the system run in summer during nighttime to cool buildings. Heat loss will also be a factor. So when you put a transparent solar collector on a wall, it also recovers the heat that's escaping from that wall. So any wall has an R value. It basically loses heat towards the environment, depending on the R factor. And you can imagine that if you put a transparent solar collector in front of it, that's going to recover the air that's passing through within the plenum, will basically take the air back into the ventilation system, not the air, but the heat escaping from the wall back into the ventilation system. Another benefit, side benefit, heat stratification. So you've seen open ceiling applications. So if you modulate the solar air so that the air delivered in the building is slightly lower than the ceiling air, what's going to happen through a strategy of airflows with the ducts that you have, you can also achieve destratification. So therefore, all the heat that's been paid for, that's going to stay around the roof and escape through the building envelope is basically brought back down, and less heat is going to be used because the thermostat's going to see again this heat coming back to its human height level. So again, destratification is another side benefit that can be attained with solar air heating. We talked about air quality. There's been many studies. These ones age, but they're still the same. Back in the 1990s, we talked about sick building syndrome. More recently, we had COVID, and COVID did show us, and ASHRAE did adjust some of its requirements and standards with COVID. And so in many places, it's a fact, basically, that we can produce, we can actually feel better in a place where there's more outside air. It's costly, but it's worth it. It's very much worth it. And so we usually talk about 20 CFM per person to increase air quality. And many studies have shown again that with this sick building syndrome or whatever that does not exist in healthy buildings, obviously, where you have okay outside air, you have like more people present and are more productive at work, obviously, than in a stale air environment. Energy modeling, regardless of wherever you are, in the States or Canada, you do a project internationally. We use a software called RedScreen. RedScreen can be downloaded by you folks, architects and engineers. You can pay a license to have like a printable version of it, but anybody can work on it and basically see, okay, if I have like 1,000 square foot here in Allentown, Pennsylvania, I have 5,000 CFM pulling in. You can type these in, and it's going to show you basically your carbon reduction, as we can see on the middle graph here, and you can also see the payback or the positive cash flow curve that comes out of the simulation. So this is a pretty neat tool, and because our collectors or the collectors that you would be using are certified, the results are pretty good. And again, since there's no R&D, whatever energy modeling you do with that, if the right parameters are put in, you're going to get the right results. So basically, by putting in an air collector, it reduces the consumption of the process that basically comes in to produce whatever you want to produce. And also, the material that is produced in the factory will have less embodied carbon because less fuel was used to produce it. So that's how it sort of creates carbon reductions. We talked about lead points, for example. So a solar air heater is a renewable energy resource. So right there, you get that first point for that renewable energy. And as you can see here, it'll either provide some points or parts of points getting there in other categories as well. So it's been also solar air collector recognized by many different associations, initiatives, recognized as a clean technology that you can see here. So so if you've been around these, you may have heard about transpired solar air collectors. They're also used, as we mentioned before, in small-scale equipment sometimes. Could be large-scale, but small-scale dryers. We can see here an example in Colombia where they can basically dry herbs and spices, coffee, whatever. So that also is used for that. You can see a transpired solar collector in a box environment tied to a dryer. There are many different subsidies available from your utility. From the federal government, there's still some things left over, and some states also encourage solar technologies. And so incentives vary. They check, you can go to this website here, and basically wherever you are, see what's available in your area, what sort of programs are available, and you look for certified collectors to fit in to do your solar thermal project, which can sometimes be, there could be financial help to achieve it. So again, transpired solar collector, perforated plate, simple. I hope to have been able to show you that it's a simple technology. You pull air through it and it's going to deliver solar heated air. Efficient, we did talk about up to 90%, usually around 80% of efficiency, that is to convert solar energy into warm air, and sustainable, because what we do is basically we heat with the sun, and we also reduce the use of combustible fuels to achieve the heat load. And in that case, I'll be 50 minutes. Yeah, so we'll be okay for questions if you have some, and I'll be happy either to read you or to hear from you.
Hi there, Christian. Thank you so much for that presentation. Give me one sec to pull up some questions here. And then if you guys haven't already, go ahead and fill out that webinar poll for us while we get through some remainder of these questions here. Okay. First one here, does cavity space between collector wall and normal outside wall have to be drained for water or dew point situations?
Very good question. So yeah, some manufacturers do provide weep holes down the bottom of the collector. The collector is a porous collector, so it will draw some water through the perforations at times. So we do expect it to get wet, basically, inside and outside, and some water may flow down to the bottom. And yes, some weep holes are used there to make sure there is no water accumulation. However, I must say I've never seen any water accumulation or rust within a collector in about 30 years in that field, but it's made for that. Yes, very good question.
Okay, it looks like we've got two more over here. What coatings work best on outside of normal exterior wall of transpire collector?
The first part of the question, please.
What coatings work best on outside of normal exterior wall of transpire collector?
Yeah, you're probably referring to the existing wall behind it, like a transpired solar collector I've seen put on bricks and cement walls, as well as sandwich walls, IMPs, there's insulated metal panels. So basically, there is no surface that is not good for a solar air heater. All we want is that surface to be airtight. So basically, we don't want the air to be drawn in from inside the building. You wouldn't want the existing wall to be old and porous. So that you got to pay attention. So in some retrofit projects, we have patched the wall, if you want, and made it impermeable to air and water before we put then the cavity and all the parts that we need to put the transpired solar collector on it. So to answer your question, any substrate or any existing wall is good for a transpired solar collector. Favorite one could be an IMP, an insulated metal panel. In that case, you have like factory made product that you put on the wall, and then you can stick or screw right onto it your solar collector, and you're done. So that could be, in terms of speed, the best. But again, all surfaces are good for it.
Okay, thank you so much. Next one is about colors. Can you match specific colors or provide samples for them? What's the standard and custom color palette?
Yeah, we often, if you ask for a sample, like manufacturers will send you typically a black sample or a selective sample. However, if you do have a project where the corporate color is dark green, for example, and you want a specific sample of dark green, you go ahead and the manufacturer will give you the absorptivity of that color, and it can actually put that absorptivity in the simulation that we use to foresee how much energy is going to be delivered by the wall. So basically the colors, as we say, the darker the better, but we've seen with white colors, we have about 35% of the efficiency that a black will give you. Well, believe it or not, we have delivered some white systems at times, and so it's a matter of aesthetics over performance in that particular case. So yeah, so anything is possible in terms of colors, but of course the most common ones are the darker ones.
Awesome. Thank you so much. Oh, we got one more that came in. Can you provide wind uplift testing data and FM approval ratings for our roof assembly?
Yes, we can. We can also like do a sample, like we do mock-ups at times also, like for testing. So if it gets to that, that can be done. But the answer is yes, like for any other metal cladding or roof that you will have on the market, for sure. Yes, we could do that. Yeah, and I think most manufacturers do that as well.
Awesome. Thank you so much. That is everything on my end for now. Oh, sorry, we have one more that came in.
Okay.
Is the top of wall allowed to be vented at times for a bypass?
It wouldn't be the top of the wall that is open for a bypass. The bypass damper, again, could be located just about anywhere. When I say anywhere, it could also be on the ducting behind the wall. So it doesn't have to be where the wall is located. It doesn't have to be really where on the surface of the wall. It could be on the sides or on the HVAC equipment. And so it's all a matter of like controlling the dampers with the right locations of the damper. The ones that do choose to have dampers on the wall, it's an architectural choice. So very often you'll have like a color matched damper that will just fit on the wall. Typically, that's how it's done. It can be on the top and center of the wall, the bypass. It could be also like down the bottom. Same with the air draw. Some people ask a second question to this is like, where do I have the draw? Is it better top and center? The answer is yes. Can it be on the far left, the far right of the panel? On the covered area, could be down the bottom. Yes, it can be down the bottom. Is it less efficient if we have it down the bottom? Yes, slightly, maybe about 15% less efficient than if you have one on the top. However, there are some ways we can do to make sure that the air that comes from the top goes to the bottom into the ducting system. So there are all sorts of ways to work around that, either for air intake locations and for bypass locations. There's a lot of options for designers here.
Great. And we have a three-part question coming in. What is the cost per square foot typically? Has it been used in New York City? And the typical thickness of the wall assembly? Let me know if you need me to repeat any part of those.
So the first one regarding like a price per square foot, it will vary very much. Again, if you do a project in New York and if you do a project in, I don't know, North Dakota with different designs, it may vary quite a bit. So the price, it varies also per manufacturer, per finish, and so on. So it's hard to say. However, we've seen fully installed from $20 to $60 a square foot, usually averaging around $30, $35 a square foot. That's what you can look at. However, be very careful with that. So what's the second part of the question, please?
Yep, it's so has it been used in New York City, which you
Yes.
answered, and then the typical thickness of the wall assembly.
Yeah, I did mention from 4 to 8 inches. Again, it's to ensure that like that spacing will make sure that regardless of where the air intake is located relative to the geometry of the wall, sometimes if it's not centered, it'll have to be on the sides. And so we have to increase at times the cavity thickness. The most I've seen is about 24 inches, and that's an exception. Again, 8 inches really covers most, I would say 98% of the different designs. So again, if you have a special design or special configuration, we can go up. That doesn't affect basically the performance of the collector. And again, that cavity is made so that it gives an even negative pressure so that all the holes are used, or all the perforation are used to pull in air. So we saw the picture with the thermography on it, and you could see that the whole collector was sort of like a cooler than the non-active part, and it also was uniform. It had a uniform finish. So we don't want the hot spots in there, which means that this area of the collector, if you have an up or left corner, for example, and it's not working, you can see that it'll be showing as hot on the picture. So if your collector is hot, it's not working. If it's cool, it's working. So that's the aim of the cavity. Again, 4 to 8 inches is standard, and very rarely do we have exceptions going beyond 8 inches thickness.
Awesome. I think that's everything on our end. Do you have any final wrapping up thoughts about ATOS or anything else you'd like to mention?
What I'd like to say again is probably transparent air collector is the probably the simplest and also the cheapest in the good sense per kilowatt hour produced of heat of any renewable energy technologies, including solar and all the other renewables that we have. So it's something that is not known by many people, but every time it's been applied, it's been satisfactory and simple to use for customers. So I would say there's a there's a community gain to know more about it. I would say it that way
Okay,
as a conclusion.
perfect. Thank you so much, Christian, for your time. I hope everyone has a great rest of their week. Bye, everyone.